Good afternoon, everybody. I greet the students at the lecture on biophysics. This lecture concerns hemodynamics, principles of analysis and modeling of human cardiovascular structures functions. The goal of the lecture is the hemodynamics modeling implementation for quantitative specification of blood flow into human cardiovascular system. The objectives of the lecture is of this list. First, it is the review of the parameters nomenclature and the basic laws of hemodynamics. The second, it is the specification of blood rheological and hydrodynamic properties. Hemodynamics analysis of blood flow through human cardiovascular system is the objective that is under number 3. Points of the lecture are listed at this slide. What are the points? First of all, it will be the review of hemodynamics parameters nomenclature and basic laws. The next, let's consider hemodynamics aspects of blood flow into human cardiovascular system. And these, as the physics methods of human cardiovascular structures diagnosis, is the third point of the lecture. And we complete lecture with summary and bibliography. Before we start the review of hemodynamics parameters nomenclature, the hemodynamics term should be defined. At a fundamental level, the study of hemodynamics is concerned with the distribution of pressure and flows in the circulatory system. In medical contexts, the term hemodynamics often refers to basic measures of cardiovascular structures function, such as arterial pressure or cardiac output. In the present lecture, hemodynamics refers to physics study of flowing blood and of solid structures blood flows through. Hydrodynamics is physics section specifying properties and revealing regularities of fluid movement. Any fluid at natural world. So then, hemodynamics parameter nomenclature is hydrodynamics parameters nomenclature renamed to determine and emphasize an object of study. It is the flow of blood through the human circulatory system. So that is why we can define the hemodynamics as application, implementation of the hydrodynamics, the section of physics, to quantify the blood flow through the blood circulatory system. So, as I said already, the review of hemodynamics parameters nomenclature should be pre-reviewed with liquids' general characteristics. First of all, about the liquid as itself. The particles that form a liquid are relatively close together. The particles in a liquid have more kinetic energy than potential energy. The liquid particles move faster in terms of vibration, rotation, and translational motion. Because they are moving faster, the particles in the liquid occupy more space and the liquid is less dense than the corresponding solid. But there are exceptions, as ice and bismuth. The ice floats in water. The force is required to arrange motion of any object. The simple experiment demonstrates how liquid can be forced and moved. This figure shows two flat plates separated by a thin fluid layer. If a lower plate is held fixed, a force is required to move the upper plate at a constant speed. This force is needed to overcome the viscous forces due to the liquid and is greater for a highly viscous fluid than for a less viscous fluid. The force F is observed to be proportional to the area of the plates. It is denoted here by A letter, and to the velocity of the upper plate denoted by letter V. And the force that is required to move the upper plate is inversely proportional to the plate separation. It is the distance between the plates that is denoted here by letter L. The ratio of the velocity to the distance between the plates is termed as the velocity gradient, and the proportionality coefficient in this equation for the force is termed as the liquid dynamic viscosity coefficient. The larger the liquid dynamic viscosity coefficient, the larger force needed to move the plate at a constant speed. Usually, as the temperature decreases, liquids become more viscous. The moving liquid is structured into parallel sliding layers, as you can see at the previous slide. The reason for gradual slowing is the friction between adjacent layers. This intrinsic property is defined as liquid viscosity. The structure of the moving liquid can be interpreted as the shear deformation. In terms of deformation, in experiment, liquid is subjected to a mechanical stress. It is the ratio of the force to the plate area. This is the stress, mechanical stress, that the liquid is under. The velocity gradient into the moving liquid is the shear rate. It is the shear rate. Newton's law of viscosity defines the relationship between the shear stress and shear rate. What is that relationship? The ratio of shear stress to shear rate is a constant for a given temperature and pressure and is defined as the dynamic viscosity coefficient of the liquid. So you can see this ratio that is constant. And one more should be mentioned here, the kinematic viscosity coefficient. It is the ratio of the dynamic viscosity coefficient and the density of the liquid. The dynamic viscosity coefficient is characteristic for liquids classification. Ideal fluid is a fluid that has no viscosity. It is incompressible in nature, and practically no ideal fluid exists. Real fluids are compressible and they have some viscosity. In turn, the real fluids may be classified into two types. Newtonian fluid is a real fluid that obeys Newton's law of viscosity. For a Newtonian fluid, viscosity is entirely dependent upon temperature and pressure of the fluid. Non-Newtonian fluid is a real fluid that doesn't obey Newton's law of viscosity. And these two graphs illustrates the two kinds of Newtonian and non-Newtonian fluids types. The kinds of liquids motion is classified as well. One of these is illustrated by the diagram of the experiment that we considered already. This is the laminar flow. The liquid in contact with the moving plate in this figure has the same velocity as the plate. You can see the liquid that is in contact with the plate moves with the same velocity as the plate. The fluid layer just below moves slightly more slowly, and each successive layer lags a little bit more, as identified by the arrows of the different lengths. The length reflects the magnitude of the liquid particles' velocities. The layers, this layered structure or laminar flow is the kind of streamline flow characteristic of viscous fluid at low velocities. Laminar flow is sustained as long as the flow velocity does not reach the critical value. When the layers begin to mix, establishing irregular, partly unpredictable fluid motion known as turbulences. It is defined as liquid turbulent flow. Turbulent flow is illustrated by this figure. In turbulent flow, some energy is dissipated as sound and some as heat. The noise associated with the turbulent flow in arteries facilitates blood pressure measurements, and it makes possible the detection of some heart abnormalities. So this irregular motion of the liquid produces the sounds, specific turbulent flow sounds that may be auscultated, and by that means a doctor can determine whether the flow of blood into the big enough arteries is laminar or turbulent. The Reynolds number determines if the flow of either a liquid or gas is turbulent, laminar, or transient. It is defined as the ratio between the liquid's internal force versus its drag force. Consider a fluid of known viscosity and density. If it is flowing in a tube of known radius and has an average velocity, linear velocity of motion, that is known as well, then the Reynolds number is defined by formula shown at this slide. Reynolds number, you can see. In tubes, it is found experimentally that if Reynolds number is less than 2000, flow is laminar. If Reynolds number is greater than 4000, flow is turbulent. If Reynolds number is between these two, 2000 and 4000, this flow is unstable, that is, may change from laminar to turbulent or vice versa. Let's consider the laminar flow more detailed. It is the lucky case to quantify that kind of the blood motion, to write down the equation of motion as it was done for the any solid, for example, translational motion. This is just the Newton's second law. Maybe written down, and this is the equation of motion that collects the reason for the motion. It is the force that is applied to the object. It includes the characteristic of the motion. It is the acceleration, and that influence of the object, its motion. It is the mass of the object. Of the object. So same may be done for that ordered kind of motion of the liquid as laminar flow into the tube. In this case, we can find that structure of the floor into coaxial sub-cylinders sliding over surface of one another. In liquid laminar flow into a tube, individual layers of liquid are shifted relative to each other, so that the speed of each layer is differs from the speeds of other layers, but that different speeds or velocities of liquid sublayers doesn't change over time. This kind of the liquid flow is called a stationary flow. The process, the motion is in progress, but parameters of this process don't change over time. And look here, it is just this slide demonstrating by how that kind of the liquid motion as laminar flow may be quantified, by how the equation of motion of laminar flow may be derived. But as in case of the solid objects, this requires the deriving of the equation of motion requires the specific characteristics of the process of the liquid flow. It is the flow rate. What is this? It is the volume that is carried through cross-section of the cylindrical tube per unit time. And the next, it is the reason, the condition for the flow of the liquid, the pressure difference at the opposite end of the tube liquid goes through. It is the pressure drop. We can say liquid goes from the area of higher pressure to the area to the end of the tube with the lower pressure, where the pressure is lower. And one more should be taken in account, the influence that motion that of or by the tube and the liquid. And this parameter collecting that characteristics of liquid and tube influencing the motion, the flow of the liquid is termed as the resistance. Is termed as the resistance. A technique called dimensional analysis shows the relation of the parameters mentioned that can be written as equation under number 3. The formula for the flow rate is called Poiseuille's law. Poiseuille's law is valid for straight rigid tubes that contain a fluid with constant flow rate and constant viscosity. Therefore, it is not strictly accurate in regard to human vascular system. Nevertheless, important principles relating flow and tube parameters remain applicable. Poiseuille's law may be simplified to a relation analogous to Ohm's law as it is shown by formula 6. You can see. An increase in pressure gradient causes an increase in blood flow, whereas an increase in resistance causes a decrease in blood flow. These two statements follow from equation from this form of the Poiseuille's law that is expressed by equation 6. The equation of continuity is one more mathematical model of laminar flow. Consider a situation where an incompressible fluid completely fills a channel such as pipe, or it might be artery, as this is shown at this figure. Then, if more fluid enters one end of the channel, an equal amount must leave the opposite end. This principle is called the continuity principle. The equation of continuity results from conservation of mass. It is shown by equation 1. Consider two sections of a tube with the constant cross-sectional areas A1 and A2. The liquid mass entering and leaving the tube is expressed by equation 2 and 3. Entering and leaving the tube, input and output. The liquid mass entering and leaving the tube may be expressed as the product of the volumes of fluid entering and leaving the tube and liquid density. For this, you can take this part of equations 2 and 3. In a time delta t, in time dt, this is very small interval of time of the observation of the liquid flow through this tube. This is not delta, but instead The D letter is taken to denote that very small, approximately very small time, very short time, very close to be the instant, very close to be the moment of time. In this time, the fluid moves at distance, as these are shown in round brackets, in equations 2 and 3. Volumes of fluid entering and leaving the tube is V capital 1 and V capital 2 equal to the products of the corresponding cross-sectional area and distance. Formula of conservation of mass can be rewritten as equation 4. After simplification, this becomes the equation of continuity, that is under number 5. Equation of continuity. The product of the cross-sectional area and the velocity, look, the average linear velocity of fluid is constant. Usually, the flow velocity is not uniform in a channel. For example, the fluid near the walls of the channel is moving at a lower speed than the fluid near the center. The equation of continuity still holds for such cases if it is written in terms of average flow velocity, linear velocity. In any system arranged in series, the flow through each vascular component must be equal to the flow through every other, unless one segment becomes progressively distended. The cross-sectional area of various vascular segments varies in the body. To keep the flow rate equal, the velocity of flow must vary inversely with the cross-sectional area for each vascular segment. Now we are ready to start the second point of the lecture. You can see the basics of hydrodynamics we considered and develop and recognize, you can recognize the hydrodynamics parameters nomenclature. What about hemodynamics? Hemodynamics aspects of blood flow into the human cardiovascular system. Blood consists of cells and liquid part, it is the plasma. These identify blood, these two, blood cells and liquid plasma, identify blood as suspension or heterogenic continuum. The amount of cells is measured by the relative volume that blood cells occupy in the blood flow. Actually, it is the volume percentage of red blood cells in blood. It is the hematocrit. Hematocrit is the major factor that changes the viscosity. It is shown at this graph, and this graph is supported by this analytical equation. It is the exponential dependence of the dynamic viscosity coefficient of the blood on the hematocrit. An increase in hematocrit requires a greater pressure to produce a given flow rate because of the increased viscosity. So that is why you can see what is the major factor determining the blood dynamic viscosity coefficient. It is the hematocrit. And now let's look and recognize some details of the cardiac muscle structure. The heart provides the driving force for the cardiovascular system. The cardiac muscle function is similar to the skeletal muscles. These muscles tissue structures differ from each other, and this difference is shown at this illustration at this figure. Look here, skeletal muscle has striated tubular multinucleated fibers. Skeletal muscle is usually attached to the skeleton, is voluntary. And what about cardiac muscle? This has striated, branched, not tubular, but branched, uninucleated fibers. Occurs in walls of the heart only. This muscle is involuntary. This is just the difference between these two. And some more details specific of the cardiac muscle structure. As it was said already, cardiac muscle present only in the heart. It is separated, it is identified as the specific, as the separate kind of the human muscles. You know that smooth muscles, skeletal muscles kinds, and cardiac muscle. This is one from three kinds of human muscles tissues. Cells are striated and branching. You can see this branching of the cells. Ends of the cells are joined by communication junctions that allow ends of the cells, you can see, by communication junctions that allow the cells to contract as a unit together. This is required to exert the greatest possible force on the blood into the heart chambers. On the blood into the heart chambers. The heart actually is two pumps in series. That is, the right and left sides are connected by the pulmonary and systemic circulations. The diagram at the right illustration shows the heart structures. Each side of the heart is equipped with two valves that normally maintain a one-way flow of the blood. Atrioventricular valves, atrioventricular valves, you can see these, and left atrioventricular valve. These valves separate the atria from ventricles. The right atrioventricular valve is the tricuspid valve, the left is mitral valve. These valves open during ventricular relaxation, it is diastole, to allow blood to fill the ventricles, and close during ventricular contraction, systole, to prevent backflow of blood from ventricles into the atria. Semilunar valves, aortic and pulmonary, semilunar valves, aortic and pulmonary. These are not shown here, actually. Nevertheless, these valves open to allow the ventricles to eject blood into the arteries during systole and close to prevent backflow of blood into the ventricles during diastole. The right ventricle pumps relatively large volumes of blood at low pressures through the pulmonary circulation. The right ventricle ejects blood by the concurrent shortening of the free wall and bulging of the interventricular septum into the right ventricle. It is the bellows function. The normal cross-section of the right ventricular chamber is crescent-shaped. If the right ventricle ejects blood against a high pressure for prolonged periods, as seen in certain pulmonary diseases, it assumes a much more cylindrical appearance, and there is a thickening of the right ventricular free wall, the right ventricular hypertrophy. The left ventricle pumps blood through the systemic circulation. It is cylindrical in shape and normally has a thicker wall than does the right ventricle. The left ventricle ejects blood by reducing the cross-sectional area of the cylinder. Thus, changes in volume are a function of changes in radius squared. The left ventricle works much harder than the right ventricle because of the higher pressures in the systemic circulation. Consequently, the left ventricle is more commonly affected by disease processes than is right ventricle. Let me remind you the muscle work done and muscle mass relation that is derived in biomechanics for the skeletal muscles. Because of much function similarity, this is correct for the cardiac muscle as well. This relation explains the great left ventricle tissue mass with respect to other heart parts. You can see this relation. The harder muscle works, the more mass it possesses or has. This is just the base to prove that relation between the work done by the left ventricle and its mass. The mass of the left ventricle is the greatest relatively with respect to other parts of the heart because of the work hard work done by the left ventricle. You can see that the physics gives you such opportunity to understand the anatomy structures of the human organism. And the next we can do as some kinds of quantification of cardiac muscle function is this. The diagram at this slide models by the graph one pumping cycle phases or steps of the left ventricle. We can draw such graph looking and that is the close loop to illustrate one completed cycle of the function of the left ventricle. It is possible to record changes in ventricular pressure and volume during the cardiac cycle, one cardiac cycle. These records result a loop which provides a great deal of information regarding the function and integrity of the ventricles. Ventricular pressure volume loop is constructed by combining systolic and diastolic pressure curves. The diastolic pressure curve is the relation between the diastolic pressure and diastolic volume in the ventricle. The systolic pressure curve is the corresponding relationship between the systolic pressure and systolic volume in the ventricle. A single left ventricular cycle of contraction, ejection, relaxation, and refilling can be visualized by combining the two curves into pressure-volume loop. And let's recognize the steps of that completed cycle. Look, let's go from 1 to 2 point, from 1 to 2 point of this loop. What does this illustrate? The cycle begins during diastole at point 1. The left ventricle is filled already with blood from the left atrium, and its volume is about, as you can see, around 140 milliliters. It is the end diastolic volume. Ventricular pressure is low because the ventricular muscle is relaxed. On excitation, the ventricle contracts and ventricular pressure increases. You can upward direction of the arrow showing the increase of ventricular pressure. Because all valves are closed, no blood can be ejected from the ventricle. So this is the isovolumetric contraction. Then let's go from 2 to 3 following the arrow. What is this? The aortic valve opens at point 2 when pressure in the left ventricle exceeds pressure in the aorta. Blood is ejected into the aorta and ventricular volume decreases. The volume that is ejected in this phase is the stroke volume. Stroke volume is ejected. The left ventricle continues to contract, and this is the reason to eject the stroke volume into the aorta. Thus, the stroke volume can be measured graphically by the width of the pressure-volume loop. The volume remaining in the left ventricle at point 3 is the end systolic volume. You can see what is its magnitude. It is around 70 milliliters. When we subtract this left volume from the initial volume of 140, we obtain this magnitude for the stroke volume. It is around 70 milliliters for the healthy person to be at rest. So now look, you can recognize that terms nomenclature that is used to describe the cardiac completed cycle. Let's continue. Let's go from 3 to 4. At point 3, the ventricle relaxes. When ventricular pressure decreases to less than aortic pressure, the aortic valve closes. Because all of the valves are closed again, ventricular volume is constant during this phase. So this is the isovolumetric relaxation. The pressure decreases, you can see, but volume of the blood remained into the left ventricle is of the same magnitude. Isovolumetric relaxation. And after this, we go from 4 to 1. What is this? Once left ventricle pressure decreases to less than left atrial pressure, the mitral valve opens and filling of the ventricle begins. During this phase, ventricular volume increases to about 140 milliliters. It is just end diastolic volume. And now we can consider the energy change of the blood going through the heart, and that energy change of the blood is just of the magnitude of the mechanical work done by the cardiac muscle. So, and how we can deal with this, how we can compute, look, not measure, but compute the amount of mechanical work done by the cardiac muscle. The amount of the work done by the heart can't be measured directly. Instead, it can be calculated, computed. The heart is actually a transducer, converting chemical energy into mechanical energy of contraction and finally transmitting that energy to the blood. The heart moves the blood, providing kinetic and potential energies that can be calculated. The equation 1 at this slide determines the average power developed by the heart in terms of the velocities and pressures in the aorta and pulmonary artery. The bars, represent the average magnitudes of that parameters. Equation 2 represents the average power developed by the heart for a steady state condition, You can see that this power developed by the heart may be computed in terms of the blood energy changes. So, and the next, what it will be the next, it is just this. The result of the cardiac muscle work done under the blood is the energy delivered, in particular kinetic energy. Blood leaves the heart ventricles with the velocities of 0.5 meter per second and 0.2 meter per second through the aorta and pulmonary artery, respectively. The big vessels split into several smaller ones, developing circulatory tree with increased resultant cross-sectional areas of branches. In accordance with the continuity principles, it is understandable why blood flows in smaller vessels. The diagram at this slide illustrates the velocity cross-sectional area dependence in accordance with the continuity principle. The velocity of blood flow is the slowest in the capillaries because of maximum cross-sectional area in the capillaries. The slow rate of blood flow in the capillaries is beneficial because it allows time for the exchange of the gases and in pulmonary capillaries and for the exchange of the gases, nutrients and wastes in systemic capillaries. Conversely, blood flow increases as venules combine to form veins, and velocity is faster in the vena cava than in the smaller veins. The cross-sectional area of the two vena cava is more than twice that of the aorta, and the velocity of the blood returning to the heart remains low compared to the blood leaving the heart. You can see this relation between the velocity and resultant cross-sectional area of branches into the circulatory tree. Note, the average velocities into the vessels are discussed now. The average velocities. Actually, there is velocity gradients into the vessels because of the friction between the blood and vessels walls. We discussed this. This is proved by ultrasonic spectral Doppler display we considered at the lecture on ultrasound scanning technique. This slide should reminds you this. You can see the highest velocity, the greatest. It is the spectral Doppler display obtained by ultrasonic scanning. And look why it is so. Nearby the wall, the blood is slowed by friction, and closer to the center, the blood velocity increases, and it is greatest at the center of the vessel. This is just the in correspondence to the theory of the laminar flow of liquid into the cylindrical tube. Blood vessels can be modeled as elastic tubes. You can see this structure of the blood vessel schematic diagram. And what will happen when blood is ejected into this elastic tube? Look here at this illustration and recognize what happens. When blood is ejected by heart into aorta, it is the extra volume moving into the vessel that is filled already. Because of the elasticity, vessel expands. You can see blood is ejected from the ventricle into aorta. Aorta is filled already, and this leads to deformation, elastic deformation of the walls of the aorta to take the extra volume, stroke volume. Aorta and arteries expand and store pressure in elastic walls. Elastic aorta recoil sends blood forward into the rest of the circulatory system. Isovolumetric ventricular relaxation, semilunar valve shuts, preventing flow back into the ventricle. Elastic recoil of arteries sends blood forward into the rest of circulatory system. You can see what happens, and we talk about the reason, about the cause for the motion, for the flow of the liquid, the pressure drop, the pressure difference. And now you can see that there is no more pressure from the ventricles wall on the blood, but instead the extra pressure is developed by the elastic deformation of the walls. of the aorta, and then that elastic force is developed by the arteries. And by that means, from segment to segment, blood goes through the circulatory system. And now we can compute that force that is exerted by the wall on the blood into a vessel. Look here. Force exerted by blood acting on a vessel. Force acting on blood vessel wall is proportional to diameter of the vessel times blood pressure. The vessel wall tension, according to the Young-Laplace equation, is shown by this formula, the wall tension, because of the force from blood on the wall of the vessel. Symbol P here is the blood pressure. T is the wall thickness. R denotes the inside radius. And this sigma with the theta letter as a low index denotes the stress or hoop stress of the wall of the blood. So you can see what is the force that is developed by the blood into the wall, and in accordance to the third Newton's law, this force is applied to the blood, resulting causing its motion. And some more specific characteristics of the systemic circulation. Blood pressure is the force of blood against a blood vessel wall. Blood pressure is highest in the aorta because the pumping action of the heart forces blood into the aorta. The figure at this slide shows that systemic blood pressure decreases progressively with distance from the left ventricle. Blood pressure is lowest in the vena cava because they are farthest from the left ventricle. Note also, in the diagram, the blood pressure fluctuates in the arterial system between systolic blood pressure and diastolic blood pressure. Certainly, we can correlate this with the action of the heart. During systole, the left ventricle is pumping blood out of the heart, and during diastole, the left ventricle is resting. You can see these specific characteristics of the pressure that are required to describe the distribution of the pressure into the circulatory system. What is this? First of all, this is the systolic and diastolic pressure. And the pulse pressure equals to the difference between these two, systolic pressure minus diastolic pressure. And mean arterial pressure equals to the diastolic pressure plus 1/3 of pulse pressure, and this mean arterial pressure is illustrated as this line going at the middle between the systolic and diastolic pressures fluctuations. Distribution of the pressure into the human circulatory system. Look, and this is proved that fluctuation of the pressure, in particular in artery, may be palpated, and prove that statement about that fluctuation of the pressure into the circulatory system. This we will consider at the first lecture, examples of mechanical waves generation and registration. Palpation of the artery wall deflections, oscillations. And these look here, more important than the systolic and diastolic pressure is the mean arterial blood pressure. What might determine the mean arterial blood pressure? One factor is the cardiac output. In other words, the greater the amount of blood leaving the left ventricle, the greater the pressure of blood against the wall of an artery. Another factor that determines blood pressure is peripheral resistance, which is the friction between blood and the walls of a blood vessel. All things being equal, the smaller the blood vessel, the greater the resistance and the higher the blood pressure. Similarly, total blood vessel length increases blood pressure because a longer vessel offers greater resistance. And obese person is apt to have high blood pressure because about 200 miles of additional blood vessels develop for each extra pound of fat. And this relation between these specific characteristics of the blood flow, mean arterial pressure, cardiac output, what is the volume of blood ejected per 1 minute, cardiac output, and resistance, total resultant resistance of the circulatory system vessels. This is just something that is analog to the Poiseuille's law. Actually, it is the equation that is based on the Poiseuille's law. It is interpretation of the Poiseuille's law, implementation of the Poiseuille's law to describe, to quantify the flow of blood within the human circulatory system. So the third point completes the lecture. What is the third point? Let's look. It is physics methods of human cardiovascular structures diagnosis. And what it will be as the example, one more example, what is that example of that physics method? It is the auscultation of turbulent flows into the structures, cardiovascular system structures. It is the method we consider auscultation of turbulent flow. And the one more, it is the blood pressure measurement by sphygmomanometer. It is one more example of effective physics methods implemented that are implemented in routine medical practice. The sphygmomanometer includes inflatable cuff, pressure gauge, and stethoscope. And look, what is actually measured? Let's recognize. When doctor measures blood pressure, the gauge shows two types of pressures: systolic pressure the blood pressure when the heart contracts, specifically the moment of maximum force during the contraction. This happens when the left ventricle of the heart contracts. And diastolic pressure, the blood pressure between heartbeats when the heart is resting and dilating, opening up, expanding. These two are measured, systolic and diastolic pressures. The procedure of the sphygmomanometry is illustrated by the next slides. The number 1 slide is this. When the cuff is inflated so that it stops arterial blood flow, no sound can be heard through a stethoscope placed over the brachial artery, distal to the cuff. The inflatable cuff is placed at this fragment of the upper arm. The air is pumped into the cuff and this stops the pressure of the air, compress the brachial artery walls and stops the blood flow through this artery segment. And look, the stethoscope is placed lower the cuff under just at the place of the brachial artery. So, and doctor listen to the sound. Doctor auscultate this part of the artery. No sound because there is no blood flow through this. The next step of the sphygmomanometry, the release of the air from the cuff. This decreases the pressure on the artery walls and provides the narrow channel development into the artery. This narrow channel is just for the blood to flow through it, to be under the greatest possible pressure. But this flow at this narrowing fragment is not turbulent. It is not laminar, it is turbulent. So it is noisy. Specific sound is produced. And this sound starts to be heard through the stethoscope. And when doctor hears the first sound, she or he looks at the pressure gauge and the pressure is taken as the greatest and placed into correspondence to the systole. It is the systolic pressure. Korotkov sounds are created by pulsatile blood flow through the compressed artery. You can see this is the turbulent flow, so consequently it is noisy and can be auscultated. So the next, the air continue to be released from the cuff. Blood flow becomes laminar and becomes silent. Because the artery is no longer compressed, and when the sound stops, the pressure from the gauge is taken, is considered as the normal lowest, it will be better to say not normal but lowest, and put in correspondence to the diastole and considered as diastolic pressure. So, and let me pay your attention to this specificity. It is not direct pressure measurement, it is indirect pressure measurement, because the air pressure in inflatable cuff is measured, but in accordance to the third Newton's law, this pressure is of the same magnitude as the pressure of the blood on the skin, and after that this is transmitted to the cuff. So these two, air and blood, are two objects subjecting one another, and this is done with the with the forces of the same magnitudes but of the opposite directions. Physics is at the core of methods implemented in diagnosis, as it is shown by this example. Okay, and what is the next? We consider the blood pressure is very important for measurement, and why it is the diagnostic information. Look here, blood pressure categories you can recognize, doctor can recognize from the list at this slide. Note, it is evidence, objective diagnostic information. This doesn't depend on doctor. This is the evidence to objective diagnostic information. You can in future exactly and nowadays doctors can make their conclusion, make evidenced conclusion about the state of the patient, about state of the patient cardiovascular system, basing on these quantities as the systolic and diastolic pressure. And look, the graph shows why it is of great importance to keep blood pressure under control. You can see the risk of developing cardiovascular disease doubles with each 20/10 millimeter mercury increase in blood pressure. So it is of great importance to control the artery blood pressure in all cases, especially in cases when the cardiovascular structures abnormalities are suspected. And look, what are the cardiovascular system complications caused by hypertension, by high arterial blood pressure. These complications of hypertension are listed at this slide: stroke, heart attack, heart failure, blood clot, aneurysm. You can see, and these you recognize at the when you learn clinical disciplines. But now I pay your attention only to this to emphasize how important is the control of arterial blood pressure. By the way, we talk now about arterial blood pressure measured into the brachial artery. But at any structure, cardiovascular system, the pressure, blood pressure may be measured, but this can't be non-invasive as the Korotkov method. If the doctor wants or this is required to measure the blood pressure into other structures, invasive procedure is required. But this Korotkov method is the method for the routine medical practice because it is non-invasive. But independently on this, as any medical diagnostic procedure, this requires the high enough skill, experience of the doctor. Mm-hmm. So, and one more slide to show you cardiovascular system complications that in turn become the reason for more serious problems. You can see kidney disease, the eyes may be under the risk, metabolic syndrome, and cognitive and memory problems. This is the second stage as the complications of hypertension. So, and what is the next? It is the summary that completes this lecture. Look, hemodynamics models are correct to apply and quantify stationary blood flow. What are that models? You should remember. This is the Poiseuille's law, quantifying stationary blood flow, and continuity equation that quantifies stationary blood flow as well. The next, the physics principles of studying blood flow allow to formulate evidence-based predictive conclusions about the influence of the state of cardiovascular system structures on the blood motion. The evidence-based parameters of the functional state of the cardiovascular system are reflected by the physics methods, auscultation and sphygmomanometry. And finally, this is the list of the bibliography. This is the list of the bibliography that can support your learning on this theme as hemodynamics, principles of quantification and diagnosis of the cardiovascular system, human cardiovascular system structures. So we finish. Thanks for your attention.